Next, we talk about additions to carbonyls. We're going to talk about a couple of examples where stereochemistry is important in those carbonyls. In these carbonyl addition products, in both cases that we're going to talk about, we're going to have multiple stereocenters formed, and we're going to be able to describe the relationship that we would expect between them. Okay, so from a mechanistic standpoint, right, this is pretty straightforward. This is your standard organometallic reaction. The organometallic adds to the carbon. Pardon me. Organometallic adds to the carbon and break the carbon oxygen pi bond, push those electrons to the oxygen. We get this. But notice that there's stereochemistry here, right? We get this syn relationship between the methyl group, the existing stereocenter, and the newly formed stereocenter at the alcohol, right? So we get the syn alcohol in this case. And so the question, of course, is why is that what we see? And so to do this, we're going to use the Newman projection, right? We're going to look at, I'm going to put the aldehyde carbon in front, aldehyde in front. I'm going to put the stereocenter in the back of my Newman projection, right? So the aldehyde is an sp2 carbon, so it's flat, it's planar. So I'm going to have the carbonyl going that way. So that's my front carbon. And in the back, I'm going to have three groups. Okay? So I have the benzene ring, I have the methyl group, and then, of course, I have the hydrogen that's back here as well. Okay? So the benzene ring is going to be perpendicular to the carbonyl, and then we're going to have the hydrogen and the methyl group. Let's see. So we'll put CH3 over here and the hydrogen over here. So this is one option. Or we can rotate this so that the benzene ring is still orthogonal to our carbonyl, only it's pointed down, right? And all that changes for us is now the hydrogen will be pointed in this direction and the methyl group will be pointed this direction. Okay, so now why does all this matter is where the nucleophile comes in, right? The nucleophile, where are we? Must add at a specified angle, right? At a particular angle to the pi bond, right? From molecular orbital theory, we know that it's adding into the anti-bonding pi orbital, right? Because we're breaking the pi bond. When the nucleophile comes in, we're breaking the CO pi bond. And so we're adding in at a particular angle to the pi bond, and that angle is the angle of the pi star orbital, right? And so there's only kind of two trajectories that it can take. It can either come in from this angle or it can come in from this angle, right? The goal of our approach is to minimize steric repulsion. Right? So choice one or choice two, right? Choice one comes past this large benzene ring, right? And so this, right, is a blocking group. This is a large enough group that no nucleophile is going to come past that. And so option one is out. We can't go past the large group. Option two clearly runs into the methyl group here, but it's a better choice than option one, right? This is going past a smaller group in the methyl group, and so that can happen. However, if we look at the other option, right, we have the option coming in this direction or coming in this direction into the pi star orbital. Once again, we have this big benzene ring out here, and so that's straight out. But this option, right, comes past the hydrogen. So coming into pi star past the hydrogen, past the smallest group, hydrogen. Right? This is the best choice. And so basically we draw our two Newman projections, we put the large group, the phenyl group is the largest group, right? We put that group orthogonal to the aldehyde, and then what we want is we want our hydrogen to be on the path of the nucleophile. And so that's this version of it. What this leads to when the nucleophile comes in that direction now is, right, our nucleophile, which is a 5-membered ring, ends up here. The hydrogen gets pushed down just a little bit. We end up with this O minus pushed down just a little bit. And then the back carbon, no reaction is occurring there. And so we end up with all of this. And notice that what we've done is we've ended up with our two largest groups, right? The incoming nucleophile and the benzene ring. These are now in an anti-orientation to each other. They're 180 degrees. We've minimized that steric repulsion. Also notice that our methyl group and our oxygen are syn to each other, right? They're both on the same side of the Newman projection, and that syn relationship is what we see in our product, right? So then with acid workup, you would get the OH there. The methyl group and the OH are on the same side of the Newman projection, so they're both going to be wedged, right? So Falcon On is the name for this, for using these Newman projections to predict this. Falcon On doesn't give us 100% selectivity. Usually you'll get a mixture of the syn versus anti-alcohol, but you almost always favor the syn alcohol, the one predicted by Falcon On, at least slightly. And you can, of course, find exceptions to this. You can maximize this if you use a particular type of catalyst or whatever. So there's other ways of keeping track of this. But this is the rationale, right? We want to minimize steric repulsion as the nucleophile approaches. And so to do that, we use these Newman projections that give us the syn results. Similarly, aldol reactions are also very sensitive to steric repulsion in the transition state. And so when we form this enolate, right, and then the enolate reacts with the aldehyde, what we get is not just, right, once again, we can draw the straightforward arrows of this process, and that's easy enough to do. But what we actually get when these two things come together is we get a very organized transition state. And this transition state is organized by the lithium. The lithium is going to coordinate to the alcohol, or sorry, yeah, the enolate oxygen, right? But it's also going to coordinate to the aldehyde oxygen. And so as this reaction occurs, we've got hydrogen here, 1, 2, okay. Okay, so what we have is where this aldehyde is I've drawn it with the hydrogen in the axial position and the R group in the equatorial position. Clearly that minimizes steric repulsion, right? Putting this R group equatorial is the sterically most favored, sorry, steric hindrance minimized version of this transition state, right? If I drew the other version of this, right? The enolate is already set. The enolate is not changing. If I put the R group up in this axial position, right? Now this is axial. This is going to interact with other things. We've created more steric repulsion than we want, right? This is a much worse transition state, right? So this is no good. We don't want this group axial. Axial is unstable. So instead we want it equatorial. So what does that mean? Well, now when the when this makes its bonds, the alpha carbon of the enolate adds to the carbonyl. Because the lithium is coordinating these two things, when we do this, we can get to a final product, and that's always going to be kind of organized in the same way. So by placing our R group on our aldehyde in the equatorial position, we've set ourselves up now to be able to look at the stereochemistry of our product, right? Hydrogen is axial, the OCH3 group is equatorial. Get that there. Here's our amide over here. This carbonyl has been reformed. And we get this, right? The lithium is up here, coordinating everything. I kind of lost my carbonyl here. Let me take another stab at that. Right. Right. The lithium is there. We still have our chair. Everything is equatorial, or the R group of our aldehyde is equatorial. And we can see that the two hydrogens, I think the two hydrogens are easier to see, but both, we could do this kind of two ways. These two hydrogens here and here, these are syn to each other, right? Both are oriented up on the, on the drawing of the product there. And so we can see that those hydrogens should, I didn't draw them in, but these hydrogens should have the same stereochemistry in our product. And then similarly, the OH and the isopropyl or isobutyl group both are syn to each other as well, and so they end up with the same stereochemistry as well, right? So once again, we usually get the syn-aldol product. Right? Lots of people have done a lot of work to kind of control the syn-aldol product versus the anti-aldol product, right? But this transition state, this six-member transition state where we put the R group of our aldehyde that we're adding in step 2, right? The R group of that aldehyde has to be equatorial. And as long as you put that R group equatorial, you're going to continually get the syn-aldol product, right? Sometimes you'll get these both dashed instead of both wedged, but that's just an enantiomer of the original compound, and that's fine. But this transition state, right, this transition state here is kind of the lowest energy transition state, the most favored one. It lowers the activation barrier the most. And it's all based on this coordination of lithium here.